craps dice that you're holding. Let's swing over here. Swing over here. And let's do experiment number 2. Experiment number 2. So we're playing craps then. Well, we're not going to play craps. I'll lose my job. But we're going to learn about the ways to play. Well, the ways you use the tools, the pair of dice to play craps. So with craps, you throw a pair of dice, you keep track of what you get. So in this time, the random variable x is going to be the sum of the pips that are shown. Sum of the pips that are shown. So before we go any further, let's make sure we agree on what the values of that random variable are. Can we agree on them? I hope we can. Can we agree? 12 is the highest.
Yeah.
What's the lowest?
2.
Snake eyes, right? We can get a 2, and everything in between, yeah? Good, good, good. So we can get a 2, we can get a 3, we can get a 4, we can get a 5, and so forth. 7, 8, 9, 10, 11, 12. Beautiful. Thank you. Very nice. What's the chance of each one?
112.
112? Seems logical. Well, actually, there's only 11. There's only 11. It's 1, 2, 3.
Right.
Because there's no 1.
So 1 out of 11.
So 1 out of 11. Vote for 111.
Yeah.
We like 111. Okay, let's put it to test. Before you start rolling those dice, I do want you to roll. I do. I want to throw up on the screen up here. Let's put the 111th to the test, because that would work, wouldn't it? 111th would work. It would sum to 100%. We know we have to have this down here, right? We know we have to have the probability summing to 1. We know that. And 111th would do the trick, because 111th 11 times would sum to 1. Man, she's saying, wait a minute, she's feeling a little queasy about that. So what I'm going to do, friends, remember the spreadsheet from yesterday? I kind of put it up on steroids. So what I've got now is, I've got 2 dice. I've got die number 1, ran between 1 to 6, and I got die number 2, ran between 1 to 6. And then down here I've got their sum. Now, because of the way it's saved, it already has a few numbers up there. That's okay. We'll eradicate that pretty quickly by holding down the F9 button. Down here on die number 1 and die number 2, you're going to see the actual results of those 2 dice. And up here, you're going to see a bar graph of the sums. You ready?
Yep.
Here we go. This is the problem with this. I actually have to. Or I hold it down for a while, and then let go. Hold it down for a while, and then let go. I'll do it like this for a while. Now, what is 1/11th? What is 1/11th? That's like 9% or something, right? Ish, 9%. It's close to 9%. 9.1111111. 0909. So I was off by 100, then 1,000, then 10,000, then 100,000.
Damn you, Sean.
Damn me and my ish. It's about 9%. Now here's the deal. How many times have I done this? My finger's getting tired. 314. That's clever. 314. Now, we were off yesterday when we did the die rolls ourselves, but we were off by like 5 and 6%. I think maximally 5, maybe even 4 or 5%. Look at the shape of this. Now, first of all, look at these down here. Are these looking the way you would expect them to look?
Yeah.
Those look almost identical to how they should look. Remember, because yesterday with the single dice, they created a beautiful pie chart almost immediately. I mean, within the first couple hundred. I'm going to hold this down while I'm talking. See if you can predict when I let go. And some of the machines will do this. Is it bouncing at all or not? It's updating. You can see it's updating, but the graphics don't update. And some of the machines do, some of the machines don't. It pisses me off when they don't. Okay, I'm going to let go.
Okay.
Predict what that curve is going to look like up top.
Oh.
The hell?
7's always going to be higher.
The hell?
At least we know we can use some.
Hell?
7's always going to be higher.
I think we're starting to stabilize, yes?
Ooh.
We're starting to stabilize. Now here's what we're going to do. I'm going to grab the stapler and the VCR and all the other 1976 technology that I've got at my disposal. Can't move it because the damn thing's stable. I'm going to move the keyboard to it. We're going to hold this thing down. And someday I'm going to take a Visual Basic class. I'm going to have a program this. We're going to let it go. We're going to let it go for a while.
So one of the dice can be anywhere between 1 and 6, and then the smaller numbers are going to give you 7.
Yes. Now we're seeing some percentages up there. I want to see if we can take what Madeline is saying and figure out what the probability of each of these things is. Snake eyes, 2 is the smallest, right? What is the chance we roll snake eyes? Well, it's about 2% by this.
Yeah.
But where is that number coming from? Grab the dice in front of you and look at it. Make snake eyes on your dice. Oh yes. Make snake eyes on your dice. Okie doke? Good? Okay, make it a different way now.
You can't.
It's a trick command. You can't. There's only one way to make snake eyes, and that's to put a 1 and a 1, and then you're done. So there's one way to do it. Out of how many ways? Here's where your project you just did will come in handy. How many ways can the first die fall? Something squared! Did you hear that? Something squared, 100% correct. What squared? Don't overthink this. It's 6 squared. Think about the very first page of your project. And I know you probably made you a little bit nauseous. When you were selecting Groundhog Days out of the two pieces of paper, it was 16 times 15. Because there were 16 and then 15. This won't be 6 and then 5. Because the first die is independent of the second one. So your first die can fall 6 ways, and your second die can fall 6 ways, which gives you a grand total of 36 possible ways for the dice to fall. Yes?
Yeah.
So it's 1 in 36. What is 1 in 36 as a decimal, friend? Roughly 3%?
Yeah.
I paused it real quick. We'll come back to it. We'll come back to it. We'll come back to it. That's just about 3%. Good, good. Oh, you know what? Let's go 0.03. That's easier to do math on, isn't it? Not that it matters. Okay, you ready? Make a 3 on your pair of dice. I'm being very commanding. Please make a 3 on your pair of dice. Friends. Sydney, you need dice. Who else needs dice? We need dice. Rocks. Hang on. Just some dice. Here you go. Here you go, Sydney. Here you go, Roxy. Okay, you made 3 one way. Do it again. Make it a different way. Make it a different way. Is this a trick command this time?
No.
You could make it a different way, couldn't you?
Yep.
I'm guessing you made a 1 and a 2, and then you made a 2 and a 1 using. And that's why I asked you 2 different colors of dice. It's easier to see. So I'm guessing if you have, for example, Angie has yellow and blue. She made yellow 1, blue 2, and then she made yellow 2, blue 1. That's two different ways, right? Good. So what's the chance of getting the 3? 2 in 36, which is about 6%, yeah?
Yeah.
It's about 6%. Yes. Good. All right, everybody ready?
Yeah.
Make 4. Ready?
Yep.
Make 4 again. You ready? Make 4 again. Can you do it?
Yep.
You do it 4 times.
You ready?
Yep.
Make 4 again. Can you? Danny's shaking her head no.
No.
Stacy's shaking her head
You
yes.
do it 44.
I don't want a fight to break out in here. Wait a minute, now she's changing her mind.
You can only do it
We can only do it 3 because why, Angie? Why?
because the 2 and the 2 are.
Remember your snake eyes argument where I said make snake eyes?
Oh, that's
Now make it a different way. You couldn't because if you're looking at a 1 and a 1, you can't. You can go like this, but that's still the same 1 and 1. Same with 2 and 2. Anytime you have doubles, there's one way for that double to show. Exactly. So there's only 3 ways to make a 4. Doubles 2, 3, 1, 1, 3. So it's 3 and 36.
So it's not.
Which is roughly, I think, now bear with me here, I think this actually rounds to 8%, I think.
It does.
Based on what Patrick said, the 2.777%. These are rounded up, and I think this one has to round down to keep it kind of balanced.
Yeah, you're right.
Fair enough. And I think, could be wrong, but let me grab the stapler real quick. Look at that. Stand close. Stand close. Stand, let's keep going. Let's keep going. We're only about 1% off at that, if that. Oh, hang on. Hit F8. Hang on. Hit F8 somewhere in there. We going? There we go. Let it keep doing its thing. Beautiful shape, huh? Beautiful shape, beautiful shape. Okay, we'll come back to it. Make 5, friends! When you're done, make 5 again. Keep making 5 until you can't make 5 no more. Arr! Are you talking a pirate day yet?
No.
I think I missed it. I didn't remember. Arr!
Okay, we'll wait for Pi Day.
Alright, we'll wait for Pi Day. I won't have you then. I'll call each and every one of you.
We'll come back.
Too bad Pi isn't used in statistics all that much. It's a shame. Shame. It can be even.
Yeah.
I didn't even realize, I'm sorry guys, once again the screen is cut short. You couldn't see what I was talking about over here with the single dice, the dice are rolling over here. I'm sorry. Keep forgetting about that. How many ways can you make 5?
4.
Good! 4! 4 36ths. Which comes out to be about 11, yeah?
Yep.
Ish? Yeah. And correct me if I'm wrong with the rounding, because I suck at that, as you guys have seen.
You know, it's actually easier, I think, to just write it down.
As a fraction.
So, well,
Yes.
Well, I mean, instead of looking at the dice and figuring it out, it's easier to just make a list.
Good. Hold that thought. Hold that thought, because it will backfire on us in a minute. In a minute. Hold that thought, though. Make some 6s, and keep track of how many ways you're doing it. I agree with you, Madeline. I totally agree. I like using dice for this very reason, but they lead us to a false sense of security about distributions because it's so predictable what they do. Then you start looking at like death rates, and it's like, oh, okay, now I can't roll dice anymore, so to speak. I have to go get data.
Right.
And it gets messier, but it also gets fun. It also gets fun. How many 6s did you get?
5.
I have a couple of votes for 5. Double 3s, 4, 2, 2, 4,
5, 1, 1.
5, 1, 1, 5. Thank you, guys. So there's 5 and 36. Is that about 14? Check my math on that one. 14, thank you, Patrick. And Angie actually voted for this one in the very beginning. She said 7's the highest. And it's apparently in agreement up here, isn't it?
Yep.
And if you look at our results up here, it's damn close to perfect agreement with that, yes? So how many ways can you roll a 7? And you see something interesting. Rolling a 7 with a pair of dice is the same. Go ahead, Patrick.
There's more ways to make a 7.
There are, aren't there? Than any other sum. 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3. That's it. It's the same as rolling any single number on a single die. It's 1 and 6, or 6 and 36. I like writing it as 6 and 36 just because that kind of jumps out at you more. Which is about 17%. Which is about 17%. I just realized something, Patrick. I'm wrong down here. This should be 5, shouldn't it? 2.7% times 2, that should be under 5%.
It's 0.055.
Oh, it is 5.5. It should be 6. I didn't carry enough. I didn't carry enough decimal digits with me. Thank you. It jumps somewhere. I guess that's it. The 6 to the 8. All right. What happens here?
Goes back down.
It goes back down. Now you can see that happening in the graph, and you can see this beautiful symmetry right here. It actually is quite nice. But count them out to make sure you buy Y. So 4, 4, 3, 5, 5, 3, 6, 2, 2, 6. We got the double 4s from the beginning, right? So there's only 5 ways there. So 5 36ths. The 5 ways for the 8 is the same as the 5 ways for the 6. It still happens 14% of the time. Please, Renee. Please.
So you're not counting the different colors this time around?
We are. What makes you say we're not? Just out of curiosity.
Well, 5, 3, and then 3, 5.
Mm-hmm. 5, 3, 3, 5, 2, 6, 6, 2, double 4s. They're all in there. That's why it seems like I'm saying something twice, but by saying it twice, I'm counting both iterations of that. It gets even more interesting with 3 different colors of dice, which we're not going to do with actually in class because you have to roll too many thousands of results to actually get it. But we'll do it with Excel, because Excel's our buddy in that respect. Let's keep it going. How about 9? What's going to happen with 9? It's going to be the same thing that happened up here with 5. There's 4 outcomes. With 10 will be 3, 11 will be 2. And boxcars, 12 is the same as snake eyes as far as likelihood. They tend to mean different things in craps. Craps is very convoluted. It's also a very fair game as far as a game of chance goes. Basically, if you roll 7, I'll come back to craps. I don't want to get into that right now. Let's figure this out first, then we'll come back to talking about craps and why it's actually more fair than roulette as far as the first roll of the game, before you start actually betting and using quote-unquote skill and quote-unquote strategy. But we'll come back to that. So these end up being the same thing, right? You got 11% here, about an 8% there, about a 6% there, and about a 3% here, which all sum up to 100%. How are we doing up here? Take a look. It's not moving much anymore, is it? It's not moving much. There's a little bit of inconsistency just based on the law of large numbers. It says that they're going to eventually equal each other. We're not quite there yet, but look at that. Now, Nick, you had an awesome vote. He said it's going to be a bell curve. If, believe it or not, it's almost a bell curve. It makes a perfect point. This is one of the only distributions I've ever seen ever that actually is a perfect 90-degree angle if you were to graph it. If you were to graph the actual probability of these guys right here, and you can see why it's perfect. It's a perfect slope. They go up by 1/36 each time. So the slope's, you know, up 1/36, up 1/36, up 1/36, up 1/36, and then down 1/36. So when it gets to the top, it maxes out, and then it drops back down again. So it's actually, it's bell-ish. It's bell-ish enough to call it a bell, but it's actually a perfect pointed shape as opposed to a bell
Is there
shape, which
another
is
name for that then?
symmetric unimodal. Not to make up a new name, no, pointy. But symmetric unimodal. I mean, bell curves are symmetric and unimodal, but they also have that idea that they fall off quick and then flatten off. These start pointed and go down to zero. Like you can't go any further. Bell curves, those bad boys go out forever in the tails. We'll study that more in like 2 weeks. But these guys actually terminate. They don't go any further. And that's the idea of a discrete versus a continuous distribution. If anybody's getting a little sick to their stomach, I apologize. We'll come back to the infinitude of certain distributions later on. I promise, I promise. Is this fair?
Yeah.
What's the average number that you're going to get when you throw a pair of dice? And while you're at it, while you're at it, can you give me a standard deviation around that average? Good. We got to vote for 7, plus or minus 3.
Or 7.
Is anybody doubting the average of 7? I wouldn't doubt the average. I think that's a perfect average because think about where you would balance this curve, huh? Think about where you would balance this bad boy. I think you put your finger right there because you got the same amount of weight on the right as the left. What's the plus or minus? What do you think? Can we use Nick's idea? It's basically a bell curve, yeah? It's basically a bell curve. Let's use that idea and kind of extract the standard deviation. And then we'll go to the TI and actually check it. I think this is a great idea. So pretend it's a bell curve. How can we use the fact that it's a bell curve to help us out in doing this? I love this idea, actually. This is fantastic.
Well, then we don't use the IQR and use 2 standard deviations.
I'm thinking since it's bellish, I love this idea. Since it's bellish, let's go out 2 standard deviations. Now the quick trick with that, of course, is it's the chicken and the egg. I'm asking you to find the standard deviation, but I'm saying go out 2 standard deviations. To which you say, to hell with you, rule. You don't know what the standard deviation is. To which you guys say, yes, but we know 2 standard deviations traps 95% of the data. Can you show me where 95%, the central 95% of that data is?
Probably 3 and 11.
I'm thinking, well, this is like 3% out here.
Yeah.
That's the extreme low. This is the extreme high. Dump, dump. How about that for 95%?
Yeah.
I think it's legit. So that means 2 standard deviations would go from 3 to 11, which is a distance of 8.
Yes.
Yeah? Now, that's 2 standard deviations. What would one value of the standard deviation therefore then be?
2.
It would be, wouldn't it? It would be 2. Now think about, make sure you can see why. Make sure you can see why. All right, we know the average is here. And we know that this and this is the average minus 2, watch this bastard move. I'm gonna call it sigma. Eh? I'm gonna call it sigma. Why am I calling it sigma?
Because this is
the
the
whole
population.
Because this is the population. It's the population. And if you don't like this being the population, you can use this being the population. Because this is actually the theoretical probability, isn't it? Yeah. But we can call it sigma. It's okay. It's definitely ish. And this guy up here, u plus 2 sigmas. Now we know that distance is 8. But the trick is, in order to get... I do that all the time with these new markers. I do that all the time. I apologize. They're shorter. They're shorter. I can't physics. To get to 2 standard deviations, we have to add a sigma and then add a second sigma.
Right.
So to get from 7 to 11, that's a distance of 4, we must have added 2 twice. So here would 1 standard deviation would stop there. And then the other, going the other way, would be mu minus little sigma. So my vote with Renee is that the average is 7, little sigma is 2. I like it. For practice, run the numbers through your TI and make sure you can extract those same values with technology. Okay, see what I'm getting at here, friends? Make sure you can extract the same values with technology in case you ever need more precision. Am I asking you to do something brand new with this?
No.
I'm asking you to do something we've done in the past. Yeah, a weighted average. Yes, yes, yes. One of our stats for sure. So I pull this down. But I love that we call it bell shaping. I think it's fantastic. It's bellish. It's bellish. But I want to see how much inaccuracy we created. I think we did underestimate a little bit. Or excuse me, maybe overestimate a little bit. Because we put area, a little bit too much area where it shouldn't have been. That's okay. That's okay. Ish. It is an ish. But in case you need more precision, we need to talk about precision. Talk about precision. We do. Alright, I'm gonna go with you guys. Do I need that? No, I saved that in Excel.
So when we go to one of our stats, are we saying like L1 and L2?
Hell yeah!
Okay.
Because if you don't, it's gonna get confused. If you don't tell it L2, it's gonna think that you rolled a die 11 times and you got one of each of those numbers. Did I say that right? Yeah, it has to be 11, right? 2 through 12 is 11. Good, good, good. Come back to that. Hold that thought, hold that thought. Renee, please, go ahead.
Are the standard deviations the quartiles?
Not in general, no. They can be. You can have each of the cutoffs be a quartile, at least within a reasonable distance, but not in general. In general, and the more skewed the distribution gets, the worse it gets. Thank you. Next.
2.4 is maybe?
There's a quicker way to do this, and I'll be damned if I remember what it is. Say that again. Say that again. Madeline, go ahead.
I got 2.41, is that?
I think I'm off, by the way.
Yeah.
I don't know. And I'm going to do this right.
I just did
536.
L4.
Nope, I skipped one. I skipped this one. This is 336. 336. Not 336.
We rounded it, I think it's like.
That's cool. I'm putting the fractions in when they do the decimals for me.
All of those. Yeah.
Nope, that's
I
5.
just did like
I shouldn't be talking and
6,
doing
you know,
this. That's my biggest problem.
686.
I am a guy. One thing at a
We
time.
got it. I see what I know.
Still.
Oh, so you're supposed to be more than
Well, only because I'm trying to get the precision idea. Let me make sure I did this right. Nope. 1, 2, 3, 4, 5, 6, 5, 4, 3, 2. I think I did it right. Hope I did it right. Let's hope I did it right.
Oh yeah, okay, that's what I did.
Stat and calc, one of our stats. Now to answer Danny's question with an example, if you press enter on one of our stats, it will give you a number. It will give you a number. It'll even give you the correct average. But the problem with this is it thinks you rolled the die 11 times and you got a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, and a 12. Which means, Madeline, this is what would have happened if you had an 11-sided die and you rolled it 11 times and got one of each side. These are the results you would see. But that's not right. This is too high. Actually, this isn't even going to be there. This is too high because this assumes that a 2 is just as likely as a 7 and a 12 is just as likely as a 7, which is why this is so wide. This needs to be smaller because more of the data is clustered near the average. Is that fair?
Yeah,
So-
except I,
Don't worry. I did it wrong here. I did it wrong here.
okay,
That's what I'm
okay.
saying. I'm saying this is one of our stats without telling it L2.
oh, okay, great.
So what I'm going to do is I'm going to go L1 comma L2.
Oh.
Now, a couple things of note. Number one, the average. It's always going to call it X bar. It always calls it X bar because your TI wisely knows that mu doesn't exist. The problem is it's not super wise because mu does exist if you're dealing with the actual empirically or at least margin of error absent probabilities. That's a terrible adjective. I just made it up. I apologize. But the idea is that we can call these truth if they're fair dice. So the average is 7. What happened here?
Well, because it's the population.
Because it's the population, there is no sample. There is no sample. That's the perfect way I want you to think about it. Because there's a mathematical explanation too, which is confusing. So I love that. Because it's a population, that's your only standard deviation. Katie, go ahead.
Mine looks like that, except it says 55.5.
If you put in these decimals versus these fractions, they're going to be off a little bit. Yeah, that's the only difference. I put in the actual fractions, so you might not have exact agreement with me, but I guess we're all getting pretty close to 2.4 for standard deviation. The reason we underestimated is because we put too much fatness in the tails. Those tails at 2 and 12 for a bell curve would be skinnier. Does that make sense? So we'd actually have to go out further to catch. So we underestimated. And we were ballparking everything anyway. We only went out technically 94%, not 95. So we underestimated in a couple ways, but hell, we got close. We got close to that too, yeah?
Oh my god.
What's the matter?
Nothing, I just try to put the fractions in like you and it's crazy.
Well, now this brings up a good point. I'm going to leave you with this. I want to leave you with this before we come back. Putting that into your TI was a bit of a, I screwed up like 5 times. I was talking while I was doing it, which is always a bad idea. There are equations for these things, for certain distributions. We're going to learn 1 or 2 of them in this class, and I'm going to try to hide them from you as best I can. For example, honestly, because they can get pretty nasty. The one for rolling 1 die, you can describe that entire experiment by saying the probability of x is 1/6. I mean, that's what it is. It's always 1/6. When x is from 1, 2, up to 6, the equation for that distribution is 1/6. So if you wanted to, you could put that in your TI and graph it, and it would just look exactly like the distribution that we graphed yesterday. For rolling 2 dice, we know the values of x are 2, 3, up to 12. We know that. The kicker with this one is you have to have an equation that goes like this. Does anybody remember what we call those from Math 111? The equations that look like that with a hard point? Absolute value. Yeah, some of you are like, I kind of remember hating that. Yeah, so it's actually an absolute value curve, and I'm going by memory here. I think this is right. It might be wrong. I think the equation, the equation for this, I think, is the absolute value. I think this is right. I think it might be this. 7 minus the absolute value, x minus 7 all over 36. I think that's right. You can try it. If that's not right, if you come up with the correct absolute value equation, you can submit it to me for an extra credit point. It might be 6. Maybe it's -6. It's close to that. Something like that. But the point is, the reason I don't teach those, these are called PDFs. And I think I want to have this in your next take-home project where you actually use Excel to generate PDFs. They're good in that respect. They're a pain in the ass to do it mathematically. The reason I don't teach this is, number one, I can't remember it. Problem number one. Problem number two is that's when statistics feels too mathematical to folks. It's much easier to grab a pair of dice and look at them and come up with the data this way. Or to look at an Excel spreadsheet that's generating probabilities for us. So, I just fill the engine and die whenever they're on the board. I apologize. Let's take 5. How's the temperature? Is it any worse? No. Is it any better? Not really. Yeah, it's about the same level of crap. It feels sticky too. It feels sticky. Yeah. All right, I'm gonna go.